So welcome everyone. Today we continue our robotics topic, and we already done the kinematic modeling of robots, and we also have talked about the dynamic modeling of serial robots, and now we will speak about the motion control of serial robots. And first we will just consider a PD controller, and next week we will talk about some kind of inverse dynamics controllers which are more accurate. So this is the 9th week, so the homework will be available soon, and this whole thing is related to the second homework related to this subject, dynamics of robots. And in this lecture, please make notes in your own notebook or sheet, and please ask if something is not clear. Okay, so as usual, so we go on with the control of robots. And let's create the title. The title will be trajectory tracking control. It don't have to be serial, but so the big title from now is the trajectory tracking control of manipulators, and this week we will deal with it, and next week we will also deal with it. And let's draw something which shows the concept. As usual, we have some kind of base, and there is a global coordinate system called x0 and y0, and there is a robot made of rigid links connected together by ideal frictionless joints. So there are several links, and finally there is the last link here, and the index of the last link was always n, and this is n-1, and this is link number 1. This is the first moving link, the second and the third. Okay, so this is an NDOF manipulator, and the n degrees of freedom can be described by a general coordinate vector, which is an n-dimensional vector. So it's described in an n-dimensional space, and these are the joint coordinates. So this is what we have so far, and we have also some other things. So we have a so-called kinematic model. It was the first iteration step in the Newton-Euler recursion to create the kinematic model, and the kinematic model is basically the ability to calculate the pose, which is the position and orientation of each link, or we can calculate the position of any point of the robot in the global system. So everything has to be calculated in this global system, and for this we can create this so-called homogeneous transformation matrix, which depends on, so this is just a reminder, which depends on every joint coordinates, okay? And it was calculated by simply multiply the neighboring homogeneous transformation matrices. There was the first one, which was transformed from first to the 0 coordinate frame, and it depends on the first joint coordinate, and then we multiplied it with the second homogeneous transformation matrix, which transforms from the second to the first one, and it depends on the second joint coordinate, and so on until the last one, which transforms from n to n minus 1, and it depends on Qn, and this is again a homogeneous transformation matrix. So we can create this homogeneous transformation matrix which transforms from here to the global coordinate system, and the aim was to be able to calculate the position of the so-called tool center point in the global frame. So we said that there is a so-called tool center point here. Okay, this is the tool center point, and its position is given by this homogeneous transformation matrix from the last coordinate frame to the zeros one times the TCP position in the last frame. So now it is time to draw this. So the last coordinate frame, x, n, y, n, and of course we have z, n somewhere, should be shown in the figure. So this position is a constant because the TCP point is always in the same place in this last coordinate frame, but this coordinate frame is moving, and this homogeneous transformation matrix represents the motion of this coordinate system. So finally we can always calculate this position in the global frame. Okay, so this is basically the kinematic model of the robot. There was a lot of details, but in a nutshell it's the kinematic model. And we also have the dynamic model, which means that we are able to calculate the accelerations from the kinematics, and we are able to calculate the joint forces and joint torques. So there were two things. So we could also use the Newton-Euler equations, or we could use the Lagrangian equation of motion. But finally, with both methods, we obtain the same. So we can obtain an equation of motion in which there is a mass matrix, and the mass matrix depends on the joint coordinates, and then there were some term, sorry, I will just put it here. So mass matrix which depends on joint coordinates times the accelerations, the joint accelerations, plus some general forces which depends on joint positions and joint velocities, so damping and spring forces and gravity, and some kind of inertial forces like Coriolis forces can be put here. And on the right hand side there is a term which represents the active forces or joint forces and torques. So together they represent, let's say, Q for joint torques, or forces. But we splitted the joint torques and forces into a distribution matrix or control input matrix times the joint forces or torques last week we have seen it in detail. And sorry, one more thing. So this can depend on Q and times U. So this is a totally general form of a manipulator like this. So this is what we have now, and let's see what is trajectory tracking control. Now we will draw two trajectories, and one trajectory will be the so-called realized trajectory on which the end point of the robot moves. Okay, so this is the so-called realized trajectory. It's not really visible. So this is the trajectory in the space on which the tool center point moves. And there is another trajectory on which the tool center point should move. So we would like to move the tool center point on this red one. This can be different from the realized trajectory, but they should converge to each other. Okay, so we can draw something where these two trajectories are closer and closer to each other. So this red one is the so-called desired trajectory. Or we can say prescribed trajectory. Okay, this is the prescribed or desired trajectory. And we want to move our tool center point in the desired trajectory. So finally the realized trajectory of the tool center point will be closer and closer to the desired trajectory. They should converge to each other. So we can summarize the control goal. So we create a control of the robot, and the goal of the control is that to find these control inputs here. So this is very important. In the control goal we would like to find the control input U in such way that the realized trajectory, the blue one, converges to the desired one. Okay, so the control goal is to find the control input U in such way that the realized, I will write it in blue, the realized trajectory converges to the desired, or in other words prescribed Okay, so this is our control goal. There is a part, like in a typical robotic application. If I want to reach an object, I have to move the robot in a certain trajectory and then grab the object and put it somewhere else. So always there is a desired motion of the robot, and we want to create a control goal which provides this desired motion. Please ask if something is not clear, but I think it should be. And let's go into some details. We can give some examples. So let's see how the desired trajectory looks like. So in planar case, the desired trajectory means that the tool center point is defined as an explicit function of time. So we say, for example, in this planar case, that there is a function of time for x, and there is a function of time of the y component, and then we just describe the desired position, and which is important, we will use this notation here. So this is a small d in the upper right corner. This is a superscript, which means that desired. Okay, so this is the desired trajectory, and this is defined in the so-called workspace. The workspace is the physical space of the robot. Okay, so one thing is that this is defined in the workspace. Workspace is the physical space, we can say. Sorry, yeah. Physical space in x and y space, and if we are in three-dimensional case, this is x, y, and z. That's trivial. And the other thing is that it is an explicit function of time. So there is, we will see some examples soon. There are some explicit functions of the time. So this is the desired trajectory, which is an important thing. And there is also one thing which is similar but not the same. People also use the term desired path, or just simply path. And path means that the functions are not defined versus time, but time is eliminated. So in case of desired path, we only know how the coordinates depends on each other. So for example, y is some kind of function of x. Okay, so this is the desired path. So in case of trajectory, when the time is propagating, you know where you have to be. So this is the desired. But in the path, you only know the shape, and you don't know anything about the time, how it's how the TCP moves along in time. You just know the shape of this trajectory, and that is called path. Okay, so these two things are different from each other, trajectory and path. And let's see an example where we really see the terms. For example, we can take any function like so here we should say that time is eliminated. While this is a parametric curve and the parameter is the time, but time is eliminated here. For example, we can say that the desired x is equal to, for example, a plus b times t. Okay, this is an explicit function of time. And the vertical component is, for example, another constant term times t squared. Okay, so this is a path like this, or trajectory like this. So in horizontal direction, goes linearly with time, but in vertical direction this is a paraboloid or something. And you can say that this is a parametric curve. And t is a parameter. T is the parameter. And this is the trajectory. And we can obtain the path if t is eliminated. So from the first equation we can say, or from the second one, it doesn't really matter actually, sorry, from the first we say that t is equal to x desired minus a over b. Okay, so t is just expressed from the first equation, and then we can put it into the second equation. So this equation and the second equation can put together, and then we say that y desired equals to c times this whole thing, so 1 over b squared times x desired minus a on the square. And you can just draw the graph of this curve. Okay, so these two things are almost the same. The difference is that the time propagation is included here, but here you don't know anything about time. You just know the shape of this trajectory, but time is eliminated. Okay, so this is the difference between path and trajectory. I think we can move on, hopefully, and we will go back and try to create some kind of control goal with which the robot follow this desired trajectory. So that would be the goal. But first, unfortunately, we have to reformulate our control goal, because we have to, or it's sometimes more convenient to formulate the control goal with the joint in the joint space and not in the physical space or in the workspace. So we will talk about the so-called workspace, which is the physical space, and the joint space next, and then we move to the control goal. Okay, and that's unfortunately necessary for us now. So first we need to talk a bit about inverse kinematics. I try to speak slowly and clearly. So the goal of the inverse kinematics is to find the joint variables with which the position of the tool center point will be equal to the prescribed or desired position of the tool center point, but I will show it in detail. So that's the main goal. So Q is the joint vector of joint variables again. but it will be much more clear if we create a drawing for this. So there will be a simple 2 degree of freedom robot to show the main idea of this kind of inverse kinematic calculation. So we say that we have a robot of which there are 2 degrees of freedom, and the first degree of freedom is described by Q1. This is a joint angle, and the second joint angle is Q2. Okay, so this is our robot so far, and this is the coordinate system which is fixed to the ground or to the world. This is the global coordinate frame, and we have the 2 center point here at the end of the robot. And we have 2 different spaces. So one is the so-called joint space, and the joint space means that if I have, for example, 2 coordinates, then this is a 2-dimensional space, and the dimensions are Q1 and Q2. Okay, this is the so-called joint space. Which only exists virtually, so this is not a physical space. And we see that we can, so this is infinitely large, but after having a whole rotation of Q1, for example, it doesn't matter if we have further rotation, so we can have this range of minus pi to pi for Q1, and also from minus pi to pi in the other dimension, which is Q2. So this whole range can be reached by the robot. Okay, and you can be anywhere. We will draw some examples. And we also have the physical space, which is also called workspace. So this is x0 and y0. These are the coordinates of the physical space, and we can draw the area which can be reached by the 2 center point. So if the arm is totally straight, then you can draw a circle with the 2 center point. So there will be a circle of radius which equals to the sum of the length of these 2 bars. So this is basically a circle of L1 plus L2. Okay, so you can reach any point on this circle if the arm is totally straight. But if you start to bend the arm, so it's more and more bent, then you can reach several points inside the circle, so you can go anywhere inside, and there is a minimum radius. So if the arm is totally bent, so Q2 is equal to pi 180 degrees. The 2 center point will be somewhere here, and there will be a smaller circle of the radius which equals to the difference of the bar lengths in absolute value. So you cannot reach the origin if the lengths are different, right? Of course, if the lengths are the same, you can reach this point also. But if, for example, L2 is shorter, then you can just reach a certain distance from the origin. So finally, this will be the shape of the set of points which can be reached by the 2 center point, and this is called workspace. And the thing is that there is a mapping between the two spaces. So in this direction it is called direct kinematics. And the opposite calculation means inverse kinematics. Or inverse kinematic calculation. And you have a mapping basically between the two spaces. For example, we can just select a point here. This will be called, for example, P1, just for an example. And P1 means that Q1 is 0 and Q2 is 0. So the robot is in this configuration. It is totally horizontal and the two bars are collinear, so the arm is straight. So if you are in the P1 point, in the joint space, you will have the corresponding point in the workspace. So the robot arm is like this, so you will reach this point. Basically, we can basically draw it. So this is the robot here. And then you can have any other point. For example, I can move here. This will be called P2. This is P2. It means that Q1 is pi, so it's 180 degrees, and the arm is straight because Q2 is still 0. Sorry, this was P1, and this is point P2 prime, and then the robot looks like this, okay? And this is basically here the fixed point. Okay, so this is the point corresponding to the P2, and so on. We can just, for fun, we can just choose any other points. For example, if both are having a pi angle, so Q1 will be like this, and Q2 is also 180 degrees, so the robot looks like something like this. So the first bar is here and the second bar is bent, so it's something like this. So this will be corresponding to point P3, and some other points, for example P4, we didn't consider this case. P4 is here when Q1 is 0, so the first bar is horizontal and the second bar has 180 degrees, so finally P4 will be here, I mean P4 prime. And let's check some other points, for example P5, when the first bar is 90 degrees and the arm is straight, so the corresponding point will be somewhere here. This is P5 prime, and here the robot is straight, but the first angle is 90 degrees. Okay, so the main thing is that you can choose any point here in the joint space, which means that you set your joint angles to a certain value, and then you can calculate the position of the tool center point in the real physical space, which is also referred as workspace. And this inverse kinematics is necessary for us because our control goal should be reformulated in the joint space and not in the workspace. So far we had the control goal, which was to guarantee that the desired trajectory given in the workspace and the realized trajectory also given in the workspace should converge to each other. But now we will define a new control goal. So the new control goal is to find the control inputs U, in such a way that the desired, sorry, that the realized trajectory for the desired trajectory of the joint coordinates Q, T converges to the desired trajectory, which is Q desired. So from now we don't speak about trajectories in the workspace, but we speak about trajectories in the joint space. So for example, if I have a 3 degree of freedom robot, then we will have a 3-dimensional joint space Q1, Q2, Q2, Q3, and there is a desired trajectory in this 3-dimensional joint space, which is not a physical space, and there will be a realized trajectory and they should converge to each other. Okay, so this is the QT, which is the realized trajectory, the real trajectory, let's say, and the red one is the desired trajectory. Okay, that's the difference. And so this new control goal is formulated in the joint space instead of workspace. And let's draw another example. So we will take this robot again. I will just clean it up here. And we will have this example of this 2 degree of freedom robot. So another example. So let's say we have the control goal or desired trajectory in the workspace, but this will be constant, so time invariant R desired T in the global coordinate system will be something simple, so it will be 0 and L1 plus L2. Okay, so it means that this robot has to be in this vertical position, because in x direction this is 0 and in vertical direction this is L1 plus L2. So we can just draw the corresponding figure. So this is x0, y0, and the robot looks like this. Okay, this is L2, this is L1, and this is the tool center point. And if we formulate the desired trajectory in the workspace, then we say that the tool center point will be here at x0 and y equals to L1 plus L2. That's very clear, I think. But we can also reformulate the desired trajectory in the joint space. but we can only do it after the inverse kinematics. So we say that the desired joint position, which may depend on time, in general it depends on time, is something coming from the inverse kinematic. But before we have seen that if the robot have to be up here, which is corresponds to P5, there is the corresponding point in the joint space, which is basically pi over 2 for the first joint angle and 0 for the second joint angle. Okay, so this means that the control goal is reformulated in the joint space. So we don't speak anymore about the workspace position. Instead, we speak about the joint positions and the desired value of the joint positions. So the important words will be underlined. So workspace and joint space are important here. So this is the new control goal, to provide this joint position. I hope it's understandable. If not, please ask in the comments and I will try to react. Okay, so from now we have the desired trajectory in the joint space, and now it is time to really speak about the control which will guarantee that the robot follows this trajectory. And we will just check two different things. The first will be the linear feedback controller. This will be the first one. This is the simplest one which one can try for any robot. So the first we check is the linear feedback controller. So again, after having the inverse kinematics, we can say that the goal is to converge the real joint trajectory to the desired one. So we have to formulate some kind of control goal with which the real joint positions converge to the desired one. Okay, again we say that these are the real joint position, and this is the desired joint position, and they should converge to each other. Or in other words, we can say that the tracking error should converge to 0. So this is another formulation of the same thing. We say that the error, which depends on time, should converge to 0 if time propagates to infinity, and the error is defined as the difference, of course, between the two things. So the error is just Q realized minus Q desired. So the difference between the real joint positions and the prescribed positions, there is an error, and this error is called tracking error. But this tracking error is in the joint space, of course. Of course, there is a tracking error which can be calculated in the real physical space, but for now we don't have to care about that for first. So this is the control ball, and we will just create a control low, and it will be familiar from the lectures on Tuesday. Or let us not just consider but synthesize. So let us create the following control low. So we say that the control input will be equal to some kind of proportional gain matrix times the error and this is familiar, I hope. And then there will be another term in which there are the derivative terms and the time derivative of the tracking error, which is basically the difference between the joint speed and the desired joint speed. So the desired trajectory for the joints are given in time, so we are always able to create its time derivative, that's clear. And from our dynamic equations we can also calculate the joint speeds, the realized joint speed. So these terms can be always calculated, and this is a very simple control law. And let's check how it works. Okay, so it is what we consider for first, and we will take some very simple examples where we see some familiar equations. So let's check what happens if we put this back to our equations of motion. So let's check the convergence. And we put it back to our equation of motion. Okay, so we put the control law back to the equation of motion. So we had that there's a mass matrix, and there is, which depends on Q, and there is the acceleration, plus there are some general forces depending on position and velocity, and this was equal to h times u. But here we will suppose that h is a identity matrix. Okay, so this is identity, and this is usually true if we are having some serial robot and we have relative joint coordinates. Okay, so this is true. This is true for serial robots with relative coordinates, relative joint coordinates. So we can say that identity matrix times u. So identity matrix don't have to be shown here, so we directly say that minus kp times q minus q desired minus kd times q dot minus q desired dot. So this will be our equation of motion if we put back the control law instead of u here. Okay, so instead of the control force, we just put our control law, and this control law was just arbitrarily find out, so we can just put anything here. So we put here the PD controller, and now let's see what happens at an equilibrium point. Okay, so at equilibrium, we say that Q is equal to some Q0, the static joint position, and Q desired will be equal to some static value again, so it doesn't depend on time. So the task of the robot is just to keep itself at a constant time invariant desired position, okay? Which means that there is no derivatives for the desired joint position. Okay, so there is no desired motion, just a static position. And we are in an equilibrium, so we also have a zero speed for the joint velocities and zero acceleration for the joint accelerations. Okay, so everything is zero. Let's go back to our equation of motion and put zero everywhere where there is speed or something. So this term will be zero because of q dot equals to zero. This term will be something. So c q0, and instead of the velocity we put here 0, and this is equal to minus kp times q0 minus q0 desired, but here everything is 0 again. So we will obtain this very simple equation, and finally we say that we see that the error will not be 0. So this is basically this is the error, and there will be an error remaining which cannot be driven to 0. So this error will be just equal to minus kp inverse, if we can calculate the inverse, times some forces. So this is not 0, and that's a problem. So if you have a simple PD controller, there will be always some kind of error. And let's see some very simple example to show that this error is not 0. So the example will be a very simple system. This is a mass block, and we are in the gravitational field, and there is a control force which tries to keep this mass block in the desired elevation, and the coordinates are just a simple q coordinate here. So this is a 1 degree of freedom system described by simply q, and we can calculate basically the inverse kinematics. So this is the inverse kinematics basically. So we say that this is x0, y0, and somewhere here there is the two center point, let's say. Okay, so the top of this mass block is the point which you want to control somewhere. And from the inverse kinematics we say that Q is equal to the elevation of this two center point in the global frame. So that's very simple. And you can say that this is the desired or anything. And from the dynamics, we have some equations. And the first equation means that we need a free body diagram for first, of course. So this is the force which tries to keep the rigid body in a certain elevation. The mass is m. There is also a gravitational force, and we assume that there is an acceleration in positive direction. So this is the free body diagram. Free body diagram. And from this free body diagram we can create our equation of motion. This is the equation of motion, which means that m times the acceleration equals to the force in positive direction minus the gravitational force in negative direction. So this is our very simple equation of motion. We can reorganize it a little bit to have this similar form. So this is m times q double dot plus m times g, which equals to 1 times u. And I just done it because I would like to show that this could be put in a general form when you have a mass matrix and then you have an acceleration term, then you have some kind of forces. For example, gravitational force, it can be dependent on positions and velocities in general. The mass matrix can also depend on positions, but now it does not depend. And then this term here is the so-called control input matrix. This is just a factor with which you multiply the control inputs. So u is the control input vector. So again you have this total general form, and we have exactly the same form, okay? And let's apply our control law. And for first, let's formulate our control goal. So the control goal is that the limit of the two center point position, which depends on q, here we see, minus the desired two center point position, which is an explicit function of time. So the difference or the error between them must be 0 if the time goes to infinity. So this is the control goal in the joint space, so in the workspace. Okay, so this is f. So y is a function of q. Here we can see. And we can also say that the control goal in the joint space is something very similar, but here we have the error between the realized coordinate and the desired q coordinate. And this should be equal to 0. So this is just a formal difference. And for the sake of this control goal, we just create a control law in this form, but now we have to apply it to our system, so everything will be much more simple. So u will be equal to minus kp, but in general this is a matrix, but now we have only one input and one error. So this is just a scalar number kp times q minus q desired and there is a derivative term which multiplies q dot minus q dot desired. So this is our control law. This is exactly the same what we have here, and let's check what happens with the convergence. So let's check if we reach this control goal, if we can drive the error into zero or not. Yeah, and one more thing. So this is that's why it's called proportional derivative controller, because this is the derivative term and this is the so-called proportional term. Okay, and let's check the convergence. And the equilibrium. So this control law will be put here into the equation of motion. That's the first step. So m times q double dot plus m times g equals to 1 times the control law. So it will be equal to kp minus times and this is minus, or we can put everything on the left hand side basically. So it's just put on the left hand side, so m times double and the gravity plus kp times q minus q desired plus kd times q dot minus q dot desired equals to 0. So that's our equation, and it looks quite good because we can just reorganize a bit. So we will say that m times everything which contains q will be put on the left hand side and everything else should be put on the right hand side. So we will say that m times q double dot plus kp times, sorry, kd will first come. So kd times q dot plus kp times q equals to everything else. So minus m times gravity will be here, minus sorry, this will be also plus kp or kd times q dot desired plus kd times q desired. So we just reorganize everything, because now on the left hand side we see that it looks like, so it could be reformulated in this reference form when x double dot plus 2d alpha times x dot plus alpha square x equals to some kind of function of the right hand side, on the right hand side. So we see that the left hand side, which is the homogeneous part, it has a stable equilibrium at x equal to 0 or q equals to 0. The homogeneous part has a stable equilibrium for q equal to 0 and kp larger 0 and kd larger than 0. So it is a happy thing that our control, our position will converge to somewhere. But the problem is that if we just check the equilibrium position, so this was the convergence of the homogeneous part, and we can check the equilibrium position. So we put again 0 everywhere which is moving. So finally we will say that kp times q equals to, so this is 0 because it's moving, this is 0 because Yeah, so it's not moving yet. And it will be equal minus m times the gravity. This is kp here, plus kp times q desired. And again, so everything which is velocity or acceleration is cancelled because we are in equilibrium. So finally we will say that q minus q desired is equal to minus m times g over kp. So there will be always some kind of positioning error, and the error does not go to zero, and that is a sad thing. The error is not zero, which means that with the PD controller we cannot guarantee our control goal. So the PD controller will have always some kind of error. And as you learned in Gábor Stepan's lecture, you can increase the value of kp and this error will be smaller and smaller, but there is a limit of kp because of the digital effect. So in order to eliminate this positioning error, there are two techniques, sorry. So one thing you can do is to increase kp, but you cannot increase it into infinity. So infinity kp would cause a zero error, but you cannot increase into infinity because there is a limit because of the digital effect. And time delay. And the other thing what you can do is to use a PID controller. So there is an integrator here, but the integrator usually also includes the problem of instabilities because of the digital effect. So next week we will learn something better. So please ask if something is not clear. And I will show something. So what we see here is that the PD controller is very similar to a spring and damper system. So it looks like a spring and this looks like a damper. So if you have purely a PD controller, for example in this example, your PD controller will behave like a spring and a damper, like a rope made of rubber. So if the gravitational force is higher, then this error will be larger and larger. Or if you are accelerating, so if the desired position is moving, then also there is some kind of elongation of the spring and damper system. So now this is the desired position, which is my finger, and the real position is the position of the ball, and depending on the external forces, this spring and damper system can have different elongations, and that's the problem if we simply use a PD controller. Okay, so the detailed solution will come next week, but now we try to guess how to solve these problems, how to eliminate this error. So now we need some ideas. We need some ideas. So the gravity should be compensated somehow. And if we compensate somehow the gravity, then this term will maybe disappear somehow. So we would like to have zero error. And the other thing what we have is that the accelerations should be also compensated. So if the desired position of our mass which means that we have Q desired double dot is not zero, we should somehow incorporate this the corresponding force in the control law. So the corresponding force should be something like m times this desired acceleration. So let's try. So we put these things together, and instead of having just simply a PD controller here, so it was the control law so far, but now we will create a new control law, and we say that U will be equal to the same. So it was minus Kp times the position error minus Kd times the velocity error, and we will have some new term which is equal to the gravity compensation, and there will be another term which will be equal to the force which guarantee the acceleration. Okay, so these two terms are the so-called feed-forward terms. And these are the so-called feedback terms. And this will be the idea of the so-called inverse dynamics controller or feedback controller, or feed-forward controller, sorry. So we say that if we check again our free body diagram of this very simple example, so this was the example that there is a mass and there is a force here and there is gravity m times g and the acceleration is upward. So it seems to be trivial that if we would like to accelerate our mass upwards, then we should apply this kind of force here, which is the m times the acceleration, and we also should have some force which compensates for gravity, like here, okay? And then on the top of it we should apply a PD controller which eliminates the small errors, And let's check what happens in the equation of motion. In the equation of motion, let's check that it was like m times q double dot equals to, or sorry, plus m times g equals to u. So it was our equation of motion. It should equal to u, but here there is kp times q minus q desired minus kd times q dot minus q dot desired, and now we have the new part of the control input, which is m times g and m times q double dot desired. So this whole thing here is the control input u. Based on the free body diagram, we can conclude that this is our real equation of motion. And the interesting thing is that these two terms cancel out, so the gravity effect just disappears. And after that, we realize that what we obtain is very nice. So finally, I have to go up here. So finally, we will have an equation. So I continue up here. We just have to reorganize it. So this will be m times q double dot minus, I will put this term on the left hand side, minus q double dot desired, and then these terms will be also put on the left hand side, so this will be kd times q dot minus q dot desired, and there is another term called kp times q minus q desired, and this is equal to 0. And you see that by adding these two terms, our error equation will be very nice. So the acceleration for the error plus kd over m times the velocity of the error plus kp over m times the acceleration will be equal exactly to 0, and it guarantees that the error will go to 0. Okay, so if you have positive kp and kd terms, then it guarantees that the limit, when times goes to infinity, the limit of the error is 0, and you can reach your control wall. So the conclusion for today is that you have some desired position in the physical space. By the inverse kinematics, you can calculate the desired position in the joint space. So you will have q desired, q dot desired, and q double dot desired. You can apply some kind of PD controller, but you will have some errors. But if you just feed forward some other terms like gravity and the desired acceleration, then you can cancel out from the equation of motion the terms which disturbs us. So finally, by adding these extra terms, which are called feed-forward terms, you can guarantee that the positioning of your control error, the positioning of your control will be totally accurate, so the control error will go to 0. So the tracking error will be final 0. And next week we will talk about the general formalism. Okay, next week. And basically in the homework you have to do something like this. So everybody will be quite familiar with this whole process after solving the homework. So please ask if something is not not clear, I will try to react. Okay, so I don't see any comments now, but later you can ask in email or in the Facebook group if it's necessary. So thank you again for your attention, and let's see each other next week. Thank you very much.